Hello, dear students. How are you? Can you hear me? Dear students, do you hear me?
Yes, we can hear you.
Okay. So, do you have any questions before we solve the problems on chapter 14?
Doctor, is it
Yes?
possible that you can do a small recap, يعني إنه general recap about the entire formulas before starting?
Yes, sure. Okay.
Thank you.
Let us do it. Okay. So I will do a summary first of chapter 14, then we start with the problems. So first, in this chapter, we learn how to apply the principle of work and energy and the conservation of mechanical energy. That's why in a first step, we need to know how to find the work of a force. And the work of a force is defined as elementary work is force dot product displacement. Why we do this? Because a force can only produce can only produce work if it's having a component along the direction of motion. So if you look at the following figure, F can be decomposed into two components, one that is tangent to the path and the other that is normal to the path. And the tangent component is the one that will do a work, while the component normal to the path will not do any work. Okay, so that's why we define the work as the dot product of the force and displacement. And in case the force is constant in magnitude and angle, then when you want to find the total work, which is integral du, no need to do integration because f and cosine theta will be constant. So you can take them outside of the integral. So if the force is not varying in magnitude and direction, is if the vector f is constant, okay, what I mean by this, if you want not vector f constant, magnitude of f constant and angle theta with the tangent constant, okay, because there is a difference between saying that the vector is constant. And here, for example, at this position, f will be, if the force f is of same magnitude and theta is the same, the vector will change direction because you have a curved motion. But in case you have a straight line, in case of a straight line, to have f magnitude constant and theta constant, you should have the vector to be constant. But in curvilinear motion, you can have constant magnitude and constant angle, but of course the vector force will change. What we care about is the dot product. So the dot product will remain the same in case the angle with the tangent line is always the same. And therefore you can say no need to integrate. The work will be F times cosine theta times delta S. On the other hand, if the angle is varying or if the magnitude of the force is varying, you need to calculate the work by integration, as we'll see in the problems that we'll go over. Okay? Now, we have several particular forces. One of them is the weight. In case you have the weight and you apply the formula of work of weight, you end up with work of weight is minus W delta Y in case y-axis is pointing upward, is positive upward. While if you take y-axis to be vertical positive downward, then the work of the weight will be equal to plus W delta Y. So whenever you have the weight, you can directly apply this formula. The work of the weight is independent of the horizontal motion. It just depends on the change in elevation. Now, we also developed, as we have seen last time together, we also developed the work of a spring on a particle. Here, as we discussed last time, they found first the work of particle on spring. So this is particle on spring. And since in the majority of cases we'll be interested in the opposite, and we need to determine in general, the particle is our system. So the work of the spring on the particle can be calculated by half K delta L1 square. Okay, please pay attention. Here it's S. You can only say that it's half K S square if you are taking the origin of S at unstretched position. If the origin is not the unstretched position, you cannot say half K S 1 square minus half K S 2 square. You need to determine delta L, stretching or compression. So the general formula that will always work, whatever is the origin of S, is half K delta L1 square, so stretching or compression at state 1 square, minus half K delta L2 square. Okay, so these are two particular forces that we face a lot. So we developed the expression of their work. So in case you have an elastic spring, elastic means you have linear relation between K and displacement, K times S. In case it's not elastic, and for example, if I tell you a spring is developing a force F equal to K times S squared, where S represents the stretching or compression, for example. Okay, then you cannot use half K delta L1 square minus half K delta L2 square. You will go back to integration. And instead of integrating KS, you will integrate KS square. And the result will be half KS cube over, not half, instead of half, you will have 1 over 3. Okay, so it will be KS2 cube over 3 minus KS1 cube over 3. This is the work on the spring, but since you are interested in the particle, you take the opposite. Yani you do 1/3 K delta L1 cube minus 1/3 K delta L2 cube. Okay? So just understand the concept, because if I vary the force, you need to go back to the concept and do integral. But if the spring is linear, you can directly apply that the work of the spring on the particle is half K delta L1 square minus half K delta L2 square. So this is
Can you please
about,
repeat
yes?
when do we use F equal KS square?
Okay. You use it if I give you in the problem. If I don't tell you it's a normal spring, in case it's not a linear spring, I should mention to you. I should give you the function of variation of the spring force with us. I can tell you, you have a spring that is non-linear and that is developing a force proportional to S square instead of S. So you can say that F is K times S square. And then if you want to find the work done on the particle, okay, you will say that the force done on the particle is minus. So F spring on particle will be minus K S squared. Okay, because when you stretch your spring, it will do on you a force in the opposite direction. So the force of spring on particle is opposing the force of particle on spring is minus Ks squared. If you want to find the work of this force, you just have to apply the formula. Work between 1 and 2 is equal to integral from S1 to S2 of minus K S square ds.
دكتور
Yes.
the difference between انه بس يكون عندنا تعطينا انت الفورس spring on the particle الفرق بس بنحط minus بس هي نفسها
هي
للبارتيكل
نفس
على spring
الفورس by action reaction. Yes.
نفس الشيء بس minus الفرق
بس
كيف؟
minus. يعني انت when you want to find the force on the spring, it's if S is positive, then the force on the spring is positive because you are
اوكي
doing
ونحن بس
that.
نجيب بس
Yes.
نحن when we are calculating the work دايما we are calculating the work للspring on the particle
صح.
not the particle on the
That's
spring
why we take the opposite. Yes. Exactly.
اوكي وانت you always mention that the spring is not linear if it's not linear
If I don't mention anything, you consider it to be linear. If
okay
not linear, I should give you the function, so you integrate.
and if it's linear always f is equal to ks
Yes. Yes. So the spring force, Ks and S should be starting, the origin of S should be from the unstretched position. Okay? يعني if the origin
otherwise الثeta أقل.
if the origin of S is here, go back to this form, half K delta L1 square minus half K delta L2 square. Because S will not represent anymore the stretching or compression.
Okay dear.
Okay. And we did together this problem in detail last time. Now, concerning the principle of work and energy, this principle states the following: that summation of work of forces between state 1 and 2 is the difference in kinetic energy between the two states. So it's kinetic energy at state 2 minus kinetic energy at state 1. So you can use this principle, for example, to find the final kinetic energy. If you know the initial kinetic energy and you know all forces acting on your system, you can calculate their work. This theorem can be used to calculate the final kinetic energy. Okay? Sometimes we know the final kinetic energy, the unknown is the displacement, for example. So we can use the principle of work and energy to determine the displacement, as we'll see in the review problems. Now, we have sometimes cases where all forces acting on the system are conservative. So if all forces acting on our system are conservative, what do we mean by conservative force? A conservative force is a force that the work of this force will be independent of the path of motion. This means I just care for the initial and final position. So if I am in position 1, for example, for the weight, I can go straight forward from 1 to 2. Or I can go up, then down, then up to reach 2. But why the work will remain the same? Because we proved together that what is the work of the weight? The work of the weight is minus W delta Y. Okay, so we just care for Y2 minus Y1. And so as long as the initial position is the same and the final position is the same, the work will be the same. This is a conservative force. This means that we are not losing energy with displacement. If you want, we just if we start from same point and end by the same point, whatever is the path of motion will end up with same work. Okay, so how we can justify this? Because when you move up, for example, okay, as you move up, you gain gravitational potential energy. But when you move down back to the same position, you will lose it again. So your energy is conserved. While if you have a friction, imagine that you have a friction. The largest distance you move, the largest energy will lose, because the friction will always oppose your motion. While for the weight, when you move up, it will oppose you. When you move down, it will help you. Okay? So the energy is in this way conserved, and we just have to take into consideration the initial and final position. While for the friction, if you move straight forward, you will lose a lower amount of energy because the path is short. But if you, of course, considering, let's say, considering if you want a certain velocity profile, okay, between 1 and 2, if you have a longer path, you will lose more energy because the friction will always oppose you. So if you move further, you will lose further. Okay, that's why we say the friction is not a conservative force, because I'm losing energy with my path. While for the weight, as long as I start and end up by same location, I can recompensate this energy. Okay, while for the friction, I cannot recompensate this energy. Once I lose it, it's lost. Okay, because always it's opposing me. It's opposing my motion, the friction. While the weight, it can help me in upward motion, and it will in downward motion. And when I move up, it will oppose me. But at the end, when I move between two positions, the same two positions, delta Y will remain the same. So I will have the same work. While for friction, it depends on my path, because the longer distance I move, the longer, the higher will be the work that I will lose, the energy that I will lose. Okay? This is the idea of conservation. So in case all forces doing work are conservative, you can apply what we call conservation of mechanical energy. And you already know how to apply it from school. You just need to know the expression of gravitational potential. For gravitational potential energy, you consider a reference line. You can take this reference line wherever you want. You have the freedom of selecting your datum wherever you want, because at the end you care for delta y. And when you replace in your conservation of mechanical energy, you will have delta y when you take y to the other side. So you don't care about the reference. You can take it wherever you want. What will change is the value of Vg, but delta Vg, when you find the variation in Vg, it will be the same wherever you select your datum. That's why you have the freedom to select your datum wherever you want, but of course it is a horizontal datum. And above the datum you have positive gravitational potential energy, and below it you have a negative gravitational potential energy. Okay. And the second force that is conservative and we are familiar with is spring. So whenever you have a problem where you have only forces that are doing work are all conservative, instead of the principle of work and energy, that of course you can still apply, you can apply in addition what we call conservation of mechanical energy. So the total kinetic energy at state 1 plus total potential energy at state 1 is equal to kinetic energy at state 2 plus potential energy at state 2. And of course here we talk about total potential energy, and if we have weight and spring, we divide it into V2 elastic plus V2 gravitational. Okay. So this is in general the main rules of this chapter, okay? And we'll practice more on it with review problems. Any question before we continue?
دكتور
Yes.
can you please go to the example بعتقد رقمه 6
Yes, sure. Yes.
this one is it possible انه تعمليه يعني please لانه
Okay. Yes, sure.
بالrecordings ما كتير فهمته please.
Okay. يلا, I will repeat it. Okay. We have two blocks A and B having a mass of 10 kilogram and 100 kilogram respectively. The question is to determine the distance as B travels from the point where it's released from rest to the point where its speed become equal to 2 meters per second. Okay, so in this problem, first we have two blocks that are connected by pulleys. This is why I tell you never separate chapters. You need to combine several chapters to solve your problem, okay? So in general, whenever you have a system of pulleys, of course, you will need to relate motion of A to motion of B. That's why the first step will be to take a datum. And here, since both blocks are moving vertically, you can take the datum to be horizontal. So I consider my horizontal datum, and I say I need two coordinates, one for block B. So this is SB. And one for block A, this is S of A. And now if I go through my chord, I have from this point to this one, I have SA plus, this is a constant. Now SB plus constant, SB another time plus constant, SB a third time plus constant, and SB a fourth time plus constant. So my equation is SA plus 4SB equal to constant. And this will allow me now to relate my velocities. So I can say that VA equals to minus 4 VB. So this is a first relation that I have. Now, if you remember, we solved a problem that is very similar in chapter 13. In chapter 13, we said that if we want to find the distance, we need to get first acceleration of blocks. So we need to apply Newton law on block A, Newton law on block B, and we get a system of equations. And then what were our unknowns, if you remember? We had acceleration of A as unknown, acceleration of B, and we have also the tension in the cable T that was unknown. Okay. And we want to solve for these different variables. Okay. So we wrote Newton law for A, Newton law for B. And since here they gave us an information about the final velocity, okay, يعني the speed, the final speed that we want to find is 2 meters per second. We had to relate acceleration to speed to solve for our system. Okay, so this is a possibility. But why work and energy will allow us to solve our problem in a much easier way? Because we have a system here. If we take it as a whole, and if we consider the whole system, why we have an advantage of considering the whole system? If we consider the whole system, the only forces doing work will be the weight of B and the weight of A. Can you tell me why? Why
What's
only?
your
Yes?
What's your question?
Okay. Why it's if I choose to solve using chapter 13, I need to solve for the tension in the cable. Okay, and I have three unknowns, AA, AB, and tension. So I have to write three equations. Of course, one of the equation will be AA equals minus 4AB by relating motion of the two blocks. And I need two additional equations, which are the Newton law on A and the Newton law on B to solve for the three unknowns. Okay, while if I use the principle of work and energy, instead of requiring three equations, I will just need two equations. The first is the relation between VA and VB, and the second is the work and energy principle. You know why? Because in case I have this system, if I take the whole system, the tension will cancel out. It will not appear in the work and energy theorem. Why? Because first, you have that the work of T on A will be opposing the work of T on B. Okay, because your power is conserved. So the work done, if you want, on A will be opposite to the work done on B. Let's say A will move up. Okay, so the tension will do a positive work on A, while tension at B level will do a negative work on B. And then these will cancel out with each other. And you can prove this. Hala will prove it together. Okay, because you have that what is work? Work is of tension. For A, let's say it's moving up, it's T times delta S of A. Okay, it's T times delta S of A. While for block B, since you have, when you take the system B, you will cut the cable at 4 locations, 1, 2, 3, and 4. So you have 40. Here at this level, you have 40. 40 times delta SB. But why I will put a negative sign? Because T is upward and delta SB is downward. So the work of tension at B level is negative. Okay, and if you look at your formula, SA plus 4SB is constant. So you can say that delta SA delta SA, but here, sorry, here why we should put, in this case, why we should put minus T delta SA, okay? Because also SA is considered to be positive downward. So when the block will move up, actually, delta SA will be negative. So delta SA will be negative and minus minus will give you a positive result. Okay, so here you should if you want, respect the coordinate direction. If you take SA to be downward, this means that delta SA is considered positive when you move down, and delta SA will be negative if you are moving up. Okay, and your tension T is opposing positive SA direction. So the general formula for the work of tension at A is minus T delta SA. Okay, so when delta SA is positive, we are having downward motion, and this will lead to a negative work, which is right because the tension is opposing motion. And when we have upward motion, the tension will have a positive work, but delta S will be negative. So minus minus will give me plus. Okay, so for both cases, I have minus the tension times displacement delta S because S coordinate is positive downward. Now, why these two will cancel out when you sum them? Because according to this relation, SA plus 4SB is constant. So delta SA is equal to minus 4 delta SB. Okay, minus 4 delta SB. So if you replace here in this equation, if you replace delta SA by minus 4 delta SB, you will get that the work of tension at this level is plus T times 4 delta SB, while the work of tension on B level is minus 4T delta SB. So they will cancel out. Okay, this work will cancel out, and no need to consider them. So you just have the work of weight of A, the work of weight of B. You have external forces here, which are the reactions at the supports, but the support is fixed, it's not moving. So whenever you have a force applied at a fixed level, it cannot produce any work. So the work at this level will be 0. Okay, so if you take the whole system, you will reduce your number of unknowns. No need, because the tension will not appear. Okay, so if you do work and energy, instead of having the unknown will be VA, VB, and no tension. So you just have these two unknowns, but you have relation between them. You relate VA to VB. Okay, and here in general the velocities are unknown, but instead of giving VB to be unknown, they gave us the velocity of B, because they said determine the distance B travel when the velocity of B will become 2 meters per second. So instead of having a velocity unknown, they gave us a distance that is unknown. So here the unknown is, instead of VA VB, is delta SA and delta SB. But of course they are related with each other, and we found out the relation between them. Delta SA is minus 4 delta SB. So we just need to write one equation now to solve for the displacement delta SA. Okay, so instead of dealing with 3 equations as it was the case for chapter 13, we just need to write the work and energy. How to do it? Okay, we say we have only 2 forces doing work, weight of A and weight of B. Let us take the whole system. How to write the principle of work and energy for the whole system? You say, I have the work of weight of A plus the work of weight of B is equal. Since you have 2 blocks, you need to take summation of kinetic energies at state 2 minus summation of kinetic energies at state 1. But since the system is released from rest, then summation of T1 will cancel out. It's 0. Okay. And what is summation T2? Summation T2 is half mass of A times velocity of A square at state 2 plus half MB times VB2 square. Okay? Now, VA2 and VB2 are known. Why? Because you have that VB2 is 2 meters per second. And we have a relation between VA and VB at any instant of time. So VA2 is equal to minus 4 VB2. Okay? So VA2 is minus 8. But we don't care for the sign because it's a square. So we don't care if it's positive or negative. So we can evaluate summation of T2. Okay? We just still have to compute work of weight of A and work of weight of B. Okay? In terms of, as we said, delta SA and delta SB are related. So since we are interested into the distance traveled by B, the only unknown will be delta SB, and we will replace delta SA in our equation by minus 4 delta SB. Let us look at the work of the weights. Okay? You have the following. SB coordinate is downward. And we said, whenever the vertical coordinate is pointing downward, what is the formula for the work of weight? It's plus W delta Y. Here, delta Y is delta SB. So plus WB times delta SB. Okay? Plus WA delta SA. So the same for A. The weight of A is pointing downward and SA is pointing downward. Okay. So since the coordinate of A is pointing downward, we can use the formula of work of weight, WA times delta S of A. Now, as we mentioned, the unknown, we have here two unknowns, but they are related. So we can replace delta SA by minus 4 delta SB. Okay? Equals to kinetic energy, final kinetic energy at state 2. So this is equal to summation of T2. Okay? And we have everything. We have everything except delta SB. Okay, we have calculated already this term, sum of kinetic energy at state 2. We have the weight of A, we have the weight of B. The only unknown is delta SB, so we can solve for delta SB. Okay? Clear?
Doctor, I do have a question.
Yes.
هلا نحن بي do move travel velocity مش هيك؟
B move with a downward velocity, yes. VB
okay,
is
okay, مش الحال.
positive, VA is negative. Because A is moving
Yes,
up,
okay.
B is moving down.
Oh, yes, makes sense.
Okay. Other
Yes, thank you.
question on this? Any other question on problems in the slides? Okay. So we continue with the review problems. Look, if you want from now on, we can do the course materials and solve problems, يعني, if you prefer this method. Okay. So instead of assigning videos for you, if you want to watch the videos before, you can do it. But I will starting from next time, I will go over all slides with you. Okay. Now for problems. Let me select the complex problems to solve them. Okay. And you can go over all problems in the recordings because we don't have time to solve all problems. These videos are collected based on 2-3 years online. So no time to do everything. But in case you tried to solve a problem and you don't know how to do it, or you can ask me during class, or you can go to the videos. Okay. So in this problem, the block has a mass m and moves within the smooth vertical slot. If it starts from rest when the attached spring is in the unstretched position at A, determine the constant vertical force F which must be applied to the cord so that the block attains a speed VB when it will reach a distance SB. Neglect the size and mass of the pulley. They gave you a hint here. The work of F can be determined by finding the difference delta L in cord lengths AC and BC. We should know how to solve without using the hint. Let us see how. So here's the challenge in this problem is the following. The challenge is that if I just consider the system of the block and I do my analysis, I can draw a free body diagram for the block. We have several forces acting on the block. We have the spring force. We have the tension in the cable. Which is equal in magnitude to F, okay? And we have, of course, the normal reaction. And since I said it's a smooth slot, no friction. Can you tell me why I considered the normal from this side and not from this one? Do I have a displacement in X direction for my block? My block is moving vertically, so no motion along the horizontal. So when I say sum of forces in X equals to 0, okay, I have F plus F cosine theta. Since F cosine, this is angle theta. Since F is pointing in positive direction, then the normal should be in the negative direction to have equilibrium in X. So this is how I can know that N is pointing in negative X. Okay, but anyway, I don't need N because the work of N is 0 since N is perpendicular to motion. So the only forces doing work here are the spring force and F. But if I take the block as a system, it will be very challenging to find the work of F. Why? Because look, the angle of F has constant magnitude, but the change in direction. So if I take its point of application on A, it will change angle with time. And then to find the work done by F, I need to perform integration. I need to relate S, variation in position, to variation in angle, which is really complex. That's why I need to think in another way. I need to take a system that can simplify my analysis. So the system that can simplify my analysis is to take the block with the cable. Why the idea of taking the cable is important? Because if I consider this whole system with the cable, what will change as forces? You still have the spring force, you still have the normal. Now you have here a reaction at the pulley, but it will not do any work because it's applied on a fixed point. But now, instead of having the application of F on a